Okay, there are two integration techniques that we need to know for Year 13 mathematics. The first of which is going to be integration by substitution. So let's say that we are trying to integrate a function, let's call it f, with respect to x. Now what we can do, similar to the chain rule in differentiation, we can introduce a new variable, which I'm going to call the letter u, to change this integral into something that we can carry out. So what I'm going to say is du by dx is going to be u primed of x. Yes, you need differentiation within an integral question. And the reason I'm doing this is because, yes, there's an x in here which I need to get rid of, but I can't integrate a function of u with respect to x. That doesn't make sense. I've got to integrate a function of u with respect to u. So I need to change the dx as well. So in differentiating u, that allows me to state dx as, in terms of du. So I can say dx is going to be du divided by u primed of x. And then I can sub this into there for my dx. So the integral, which I'm going to call the letter I, becomes the integral of f of x with respect to u divided by u primed of x. A bit of tidying up, I can say that's equal to the integral of f of x divided by u primed of x du. And then, depending on the form of this, the x's may cancel, or I may need to use my original substitution in here to give me a function of u. So that will become an integral of a new function, u, with respect to u. So this maybe was one I couldn't carry out, but in doing this substitution method, I arrive at a different integral, which I then can carry out. So this gives me g of u plus a constant of integration, and then I would sub my x back in here to give me g of u of x plus c. So I get a function of x plus c, and that's the premise behind integration by substitution. You introduce a new variable, you run it through the integral, and you come out with an integral you can do, and then you do it. Okay. So let's see this method in action. I think that's probably best. So I've got a few examples. Example number 1, let's integrate 5x minus 2 to the power of 6. Now, this is one you could do using year 12 maths, but that would require the binomial expansion. We're going to avoid that by using a substitution method. So I'm going to introduce u, which in this case is going to be 5x minus 2. And once you've done quite a few of these substitution questions, what you substitute becomes fairly routine, fairly easy to choose. So du by dx therefore is 5. Okay, it's differentiating my u with respect to x. And that tells me that my dx is equal to du over 5. And that's not really mathematically sound because du by dx isn't technically a fraction, it's notation, but it behaves in every way like a fraction. So I can replace the dx with a du on 5 in my integral. So my integral is now going to become the integral of not 5x minus 2 to the 6, but u to the 6. Because 5x minus 2 is u, so that's just u to the 6. And the dx is du on 5, so it's du divided by 5. And now this is just a year 12 integral, which I could just carry out. So add 1 to the power, divide by new power, that's going to be u to the 7 divided by 35. And don't forget your constant of integration. That's of course in terms of u, but I want it in terms of x, so I just sub my u back in, and I end up with 5x minus 7. Minus 2 to the power of 7, all divided by 35, plus my constant of integration. And that's the answer. Okay, example number 2, very similar, except this one couldn't have been done by year 12 methods because it's got a surd in there. But in exactly the same way as question 1, I'm going to make the substitution of what's inside. So in this case, it's x plus 1. So in this case, du by dx is 1. which means du equals dx. So the integral becomes the integral of the square root of u with respect to u, because dx equals du. Don't forget that's u to the power of a half, so when I come to integrate it, I can replace that with a half, and then I can apply the power rule, which is add 1 to the power, divide by new power. So it's going to be 2/3 u to the 3/2, and then plus c. Don't forget, I need to put it in terms of x, not in terms of u, so I must put my u substitution back in. So I get 2/3 x plus 1 to the 3/2 plus my arbitrary constant. And there we go, that's the answer. This one here, it's not necessarily obvious that you need to use substitution. If you were to differentiate x sine x squared, you would use a product rule and then perhaps use the chain rule to differentiate the sine of x squared. But actually, when we come to integrate, we use a single substitution. And the substitution is u equals x squared. In the two previous examples, du by dx has been a constant, but it doesn't have to be. We can see here du by dx is now a variable. And when I make dx the subject, I get du divided by 2x. Now when I plug that into here, the nice thing about this question is the x here will cancel with the x here. This question was engineered to illustrate this. So we've got x times sine of x squared, but I'm going to write that as u, times dx, but dx is du divided by 2x, and the x's cancel, so that's just a half times the integral of sine of u du. Okay, this is now an integral that we can do. It's one of the standard ones that I did in my previous video. So sine integrates to negative cosine, so that is negative a half times the cosine of u plus c. And then don't forget to replace the u with x squared. So I'm going to put c minus a half times the cosine of x squared. That's it. Example number 3. Sine of x times e to the cosine of x. Again, it's not obvious at first sight what substitution you need to make, but once you've done a few of these, we can see how it's going to work. In this case, the substitution is u equals the cosine of x, because du by dx is going to be a sine, and that's going to cancel with the sine at the front. So du by dx is minus sine of x. So that tells us that dx is going to be du divided by sine of x, minus sine of x. So we end up with the integral being the integral of sine of x times e to the u times dx, which is du divided by minus sine of x. Again, you can see the sine of x's cancel, and we're left with the negative of the integral of e to the u du, which is minus e to the u plus c. And of course, the final step, don't forget to put it back in terms of x. So it's going to be c minus e to the cos of x. And that's the answer. Fifth example, tan of x. So if I write this as the integral of sine of x divided by the cosine of x with respect to x. Again, it's not obvious what the substitution is, but u is going to be cos x again, because then in the du by dx, which will be minus sine x, the sine x's will cancel. So we end up with dx is going to be negative du divided by sine x. So the integral is going to become the integral of sine of x divided by the cosine of x, which is my substitution, u, times negative du divided by sine of x, which is negative the integral of 1 over u du. This one was one of the integrals that we looked at again in our previous video. It is the natural log of u. Don't forget your constant of integration. Now the integral symbols have gone. And now we should sub that back in. So that is going to be minus the natural log of the modulus of cos of x, which I didn't mention in my previous video, but actually it should be modded because 1 over x can be negative, but log can't. So we should pop a little mod in there, and then plus c. But using a log law, that can come in as a power. So it'd be cos of x to the power minus 1, which is sec of x1 over cos. So it's log of sec of x plus c, and that's typically how you would see it written in any formula book or online. The integral of tan of x is the natural log of sec of x. And one final example here. We've got x divided by 2 minus x. So I'm going to introduce a new variable, which is going to be 2 minus x. It's the denominator. So du by dx is minus x. Oh, sorry, is minus 1. Apologies. That tells us that dx is going to be equal to minus du. So the integral will become the integral of x divided by u times negative du, which is minus the integral of x over u du. Now this one I've included because I need to make use of this substitution a third time. You always have to make use of it twice, once to make the substitution in the integrand and once to get rid of the dx to turn it into a du, but now I'm still left with an x, so sometimes we need to use this a third time to get rid of that x in there. And I'm going to say that x is actually equal to 2 minus u du, over u du. And that's just rearranging this to make x the subject. X is going to be 2 minus u. So I've just replaced that x with 2 minus u. Almost there now. That's going to be the negative of the integral of 2 over u minus 1 du, which I can then swap those around and get rid of the negative at the front. So it's 1 minus 2 over u du. 1 integrates to u, because I'm integrating with respect to u, and the 2 over u will integrate to 2 times the natural log of mod of u. And then now my integral symbols have gone, I should include my plus c. And finally, I just put my u back in. So that's going to be equal to 2 minus x minus 2 times the natural log of 2 minus x modded plus c. And I'm just going to tidy up a tiny bit more. I'm just going to combine the 2 and the c into one arbitrary constant, because that 2 isn't actually doing anything there. So I'm going to call it c1 minus x minus 2 times the natural log of modulus 2 minus x. Okay, because c is arbitrary, I can redefine it as a new constant. And because I've done that, I should just state my redefinition. So I'm going to say c1 is equal to 2 plus c. If you don't redefine it and you just leave it as this, that's not the end of the world. But if it was a show that question where it had this as the answer, then you might get to this and think, oh, I've got something different. But actually, it is still correct. You just need to redefine the arbitrary constant to get to the answer. Okay. Don't forget that if you do redefine the arbitrary constant, you have to be all constants in there. You can't have any x's in there or any u's, because those are variables. Okay, it's an arbitrary constant, therefore it can only be redefined as a constant. Okay, yep, next video is integration by parts. Thanks for watching.